Hi everyone. I think we'll start today's lecture. As I mentioned in the email, because of the COVID, so we switched to the virtual lecture. And the plan of today's lecture is we will continue to discuss statistical mechanics for the interacting free systems. In the first two lectures, we'll focus on the content of the statistical mechanics. And in the last lecture, I will show or have some discussion about the midterm exam. Okay, so after the discussion of the midterm exam, I think you will have some feeling about the answer I want you to have. And then I'll leave some time for our TAs to have some discussion with you. Like if you have any questions about your grades or anything, you can just ask the TA. Okay. And since we are doing lectures online, so when I'm saying something, I might not see you raising your hands. So if you have questions, you are welcome to unmute yourself, or you can just type in the chat room. So I will try to answer them when I see it. Okay, so let's start today's lecture. So today the goal is to apply the statistical mechanics framework to study interacting free system. So before that, let's try to do a review of the ensemble theory. Okay, so what exactly is the information or the structure that ensemble theory tells us? So basically what ensemble theory is trying to provide is that if we have a microscopic state or a microscopic configuration, we want to know what is the probability for that particular state or configuration. So for a given C, we might have some physical constraints. And the ensemble theory basically gives us a framework to construct the corresponding probability for that microscopic configuration C. It's basically denoted as P C. Okay. By the way, why do I want to give this review? Because I want to show that what we have discussed before the midterm is basically the fundamental framework for statistical mechanics. And in the later lecture, we will basically apply those fundamental structure again and again, which means that if you understand how to operate based on this theoretical framework, you can apply this idea to study various different systems. Then basically, the later half of the semester, we'll study or discuss the applications of statistical mechanics using different examples. So it might be more interesting, so you know how statistical mechanics work to give you some predictions. But also, it means that if you understand the fundamental procedure to apply that, basically the procedure to use statistical mechanics to study different problems are basically the same. So you just apply it again and again and again. So that's why I'm going to do the review of ensemble theory. Okay, so let's back to the discussion of the ensemble theory. So the most important thing is that we want to get this probability distribution for different microscopic state. Because once we have that, we can use it to calculate the expectation value of certain observables or the fluctuation for these observables, or connect to thermodynamic potentials such that we have a thermodynamic theory to give us different descriptions such as the state equation. Okay. So in the past lectures, we basically discuss what are the physical constraints. Okay. So for the microcanonical ensemble, basically the constraint is the energy is fixed. Okay. And the corresponding probability for this constraint is the probability for each microscopic configuration are assumed to be equal with each other. So they are equal weighted. Therefore, the probability is basically the inverse of the configuration number, or the inverse of the phase space volume. Okay. And then we said that there are other scenarios that are physically relevant. So one of the scenario that is physically relevant for us is the situation when temperature is kept fixed. That is the canonical ensemble. Here, the temperature is fixed. Okay. So how to have a fixed temperature? In the lab, we just provide a heat bath, and then this heat bath is in contact with our system. And because the heat bath is huge, so the temperature is basically fixed by the heat bath. And we ask, what is the probability for the microscopic configuration? And it turns out we basically found it is proportional with the Boltzmann factor. And here, E of C is the corresponding energy for the microscopic configuration. And the Z here is the partition function. And the method to fix this partition function is the normalization condition of the probability. That's basically the sum of all the probability of different microscopic configurations should be 1. Okay. And in addition to the canonical ensemble, we discuss another useful one, which is called the grand canonical ensemble. And here, in addition to the fixed temperature, how to exchange particles with the heat bed, which means that the parameter that is kept fixed is the chemical potential. And the probability for the microscopic state is described in a very similar fashion, but now the Boltzmann factor is modified by another factor that's related to this beta mu times the particle number n. Again, the grand canonical partition function is fixed by this normalization condition of the probability. Okay. So we said, all these different ensemble can actually be understood using the generalized ensemble scheme. Which just means that you can generalize this notion that maybe you can have fixed temperature or fixed chemical potential or fixed pressure, depends on what kind of physical scenario you are facing. You can generate the corresponding probability description. And why it is so important to get this probability distribution is because the expectation value or the physical observable is basically simply described by this kind of average process. Okay. So in this generalized ensemble framework, the probability is actually proportional with the intensive variable that are keep fixed and the corresponding extensive variable of the system. And once we know the probability is proportional with this factor, we can construct the partition function correspondingly by the normalization condition again. Okay. And we say why it is so important to get the partition function, because the nature log of the partition function is related to the thermodynamic potential. So for example, if we are talking about the canonical ensemble, we will have the energy here, and here's the entropy. and this is the corresponding F and X for canonical ensemble. And if we are thinking about the grand canonical ensemble, we will have a fixed chemical potential and the particle number. And again, this one is the intensive variable. Let's keep fixed. And N is the extensive variable. Like it's allowed to exchange with the bath. And you can add other things according to your need. So let me try to be more precise. So for the canonical ensemble, the corresponding thermodynamic potential is the Helmholtz free energy. If you take this expression, the Helmholtz free energy is actually the internal energy minus the temperature times the entropy. By the way, I think there should be a Kp. Okay. So once we got the partition function, it naturally connects with the thermodynamic potential. Okay. And why thermodynamic potential is so important? Because it can lead to some measurable quantities, such as specific heat, compressibility, and other measurable quantities. But as we mentioned, statistical mechanics provides more because we have the full information of this probability of the microscopic configuration. So it also allows us to calculate something such as the fluctuation or the correlation function from the statistical point of view. Okay. So now I'm going to write down the standard process to analyze a system using statistical mechanics. Okay. So at this moment, I'm just going to tell you the procedure without asking too much about the framework of statistical mechanics, because that's what we have discussed before the midterm exam. I'll just write it down. So I hope things can make more sense. So usually when we want to analyze a system, what we have in mind is actually a physical system. Okay. So for example, maybe you have a piece of material. Or something. Okay. So at the left half column, column, sorry. I'll just write down the abstract idea, and I will write down the specific example at the right hand side. Okay. So for this system, maybe what we have is a piece of magnetic material. Okay. So the second step to study this piece of material, what we need to do is to model the system using some physical arguments to identify what are the corresponding relevant microscopic degrees of freedom. Okay, so let's take our magnetic material, for example. If we want to study the magnetic property for the system, and we want to identify what are the important microscopic degrees of freedom, it is very naturally to imagine that in this material, maybe there are a bunch of little magnetic moments pointing in various different kind of directions. Okay. However, maybe this model represented by these little vectors is reasonable, but maybe it is still too complicated for us to discuss. So we can make further simplification, assuming that these little magnetic moments at the atomic level can only point in upwards or downwards. So we model our system, and here is the grid. That's like the array of these atoms, and at the crossing point of these arrays, we will have some magnetic moments that can point in either upwards or downwards. Here I'm just randomly draw configuration. And the fact that this spin is now assumed to pointing only upwards or downwards, that's what people call the Ising spins. And these little spins are usually represented by sigma I, and it can only be +1 or -1. And here we are assuming the magnetic moment to be like the correct unit of magnetic moment. For example, maybe the ball magneton. Okay, so that's the second step. We identify the corresponding degrees of freedom. And then we probably also need to identify how these little degrees of freedom interact with each other. Okay, so that's the next step. And basically, this question is basically we want to ask, what is the energy for microscopic configuration? So the second step is basically so second step is identify Kc, and the third step is basically what is E of Kc. Okay. So here I'll just write down the example, particularly for magnetic system. It is called the Ising model. And here SZI is the little magnetic moments. Basically, you can think of it as some kind of bone magnetone times this sigma I. Okay. So the first term just basically says we want to model how these two magnetic moments interact with each other. When J is greater than 0, which means that the two spins prefer to align with each other to minimize the energy. On the other hand, when J is negative, the two spins want to arrange themselves as anti-alignment in order to minimize the energy. So J greater than 0 is the preferred direction. When J is smaller than 0, anti-alignment is preferred. And usually this type of coupling is called ferromagnetic. And when J is smaller than 0, it is called anti-ferromagnetic coupling. M stands for. Okay. And the last term basically is how these little degrees of freedom interact with external control. For example, this H correspond to the external magnetic field. Okay. So usually that's the steps. So 2 and 3 are basically a pack, because once you identify what are the corresponding microscopic degrees of freedom and you specify how they interact, basically will tells you what is the energy for each microscopic configurations. Okay. So the next step from the statistical mechanics is that we want to pick an ensemble that is convenient for us. As I mentioned, most of the time, we study a system with fixed temperature. So usually the default choice is the canonical ensemble. Okay. And here, because at step 2 and step 3, we already know what is the corresponding energy. So we know the probability for the microscopic configuration in the canonical ensemble is described by this expression. Okay. And again, this partition function is something that we already defined, so I was not going to write it down. Okay. Maybe I'll write it down because it requires us to really do some calculation. Okay. So how to justify the ensemble theory is basically what we have discussed during the midterm. So to some extent, we are discussing the origin of these ensemble descriptions. If you do not really understand the origin of this theory, but you still want to apply statistical mechanics, you can follow this machinery even without really deep understanding, but you can still get some very useful information. Okay, so are there any questions so far? Okay, so if not, I'm going to post some questions here. The first question is actually about this modeling. It's question number 1. How to do the modeling in real system. Okay. It turns out usually it requires some experience and some physical arguments. and most importantly, gas. Okay. So at this moment, I want to emphasize one point. There's nothing wrong to be wrong. So in this example, usually what's happening is that you try to identify the possible microscopic configuration, and then you try to construct the corresponding energy for these microscopic configurations. And then maybe you will make some prediction based on statistical mechanics. Those predictions could capture some phenomena qualitatively correct, but maybe not quantitatively correct. And some of the phenomena might even be qualitatively incorrect. So what do you do? What you can do is that maybe you can modify the potential microscopic configurations. For example, in this model, we only identify the magnetic degrees of freedom in our system, basically these little moments. But in the real material, it is possible that these atoms might vibrate nearby its equilibrium position. So in some case, you might need to include those vibrations into your considerations. Okay. Whenever you introduce new degrees of freedom, then you need to ask how these new degrees of freedom interact with your original degrees of freedom. For example, these little moments. So your Hamiltonian will also need to be modified accordingly. And that will lead to your final predictions need to be modified. So what usually happens is that you start from a simplest guess, and then you make some predictions, and some of the predictions is wrong, then you include other ingredients and modify your model and iterate this process until you are able to make some physically sensible predictions and compare with the experiments. Okay, so that's the potential complication of this process. And the second big question is right here. Okay, by definition, the partition function looks like that. That's no problem. But in reality, to really calculate this summation of these Boltzmann factors with different microscopic configurations are actually difficult. Only for very special situations, we are able to do the calculation explicitly and get the exact result. So the second question is, and the answer is for generic interacting systems, we usually cannot get this partition function. Okay. However, for non-interacting systems, we might be able to get it. Okay. So that's why in the following, we will need to introduce some of the very important examples for these non-interacting systems. Because in order to understand the more complicated interacting systems, it will be very helpful if we can find a non-interacting system to start with, and then consider the interacting effect as some kind of perturbation. So what we are trying to say is that if we know what happened at the non-interacting limit, and we try to turn on the interactions in a theoretical idea, then maybe we are able to reach the point where we are able to describe the physically relevant systems. Okay, so that's one possible way to go. But this path is not always working. Sometimes there are some effects that is basically non-perturbative. Okay, so if it is non-perturbative, usually that means there are some and you cannot go from the non-interacting limit to capture these non-perturbative effects. So maybe it makes sense to give some example. For example, the Fermi liquid theory. So let me start. The Fermi gas might be something at this point. And Fermi gas is a simplification that we assume the electrons basically did not interact with each other. So there's no Coulomb interaction most of the time when we study the Fermi gas. Okay. So what are the physical relevant systems? Basically, for example, like a piece of metal. Okay. We know in the metal, those electrons interact with each other like crazy. However, to some extent, at least from the general physics point of view, we still pretend as if the electrons did not have the Coulomb interaction with each other. And here, the corresponding theory is called the Fermi liquid. And to some extent, if you turn on the Coulomb interaction in a perturbative fashion, you can actually get this Fermi liquid idea. Okay. But there are something that you cannot get starting from the Fermi gas. That something is like superconductivity. Okay. So it is not obvious at this moment why superconductivity is very different with Fermi gas, because we never really introduced what that is. But I just want to mention that there are examples where understanding the non-interacting limit is actually very useful. But there are also examples that if you understand the non-interacting limit, actually it cannot help you too much. Okay, but still, it is very important for us to know or to learn the non-interacting models first, so that we can at least have something to start with to understand the generic interacting systems. Okay, so are there any questions about the logic that I just described? Okay, so if not, I think I'll stop here and take a 10 minutes break, and we will start our lecture 2:20. See you after 10 minutes. Okay, so now we should start our second lecture. So now we kind of motivate our understanding of statistical mechanics system by saying that or by explaining what's the procedure for us to describe the mechanical problem. Okay, so basically there are 4 steps. We identify our system that we are interested in, and then we identify what are the corresponding microscopic degrees of freedom, and then we identify what is the corresponding energy, which is the important information for us to form the ensemble theory. For example, in the canonical ensemble, it will tell us the probability is basically proportional with the Boltzmann factor, and it will also tell us the important object, which is the partition function. And we also emphasize during this procedure, we might encounter several difficulties. One is about the correctness of the modeling, and that could take some experience or some physical arguments to make it right. And most of the time, they are iterated between the theoretical physicist and the experimental physicist. Okay. And the second obstacle is usually the obstacle for theoretical physicists. That is, after we do the modeling, can we really construct the corresponding partition function? And it turns out that the answer is quite non-trivial. For generic interacting systems, usually the answer is no. And for the non-interacting system, the answer is maybe we can do that. Okay. So so we will discuss the non-interacting system from now and see why this answer is maybe. So the interacting free systems. Okay. So what do we mean by that? Okay. So remember, in the first step, we will need to identify the microscopic degrees of freedom. For example, in the ideal gas, we have the position and momentum of the particles. In the magnetic system, we have the orientation of these little spins, and it could be plus or minus 1, and etc. Okay. So for those system that is considered to be interacting free, it means that there's no coupling between those microscopic degrees of freedom. Okay. Here I'm just going to use 2 examples for the particle systems and the spin systems. So for the non-interacting case, or the interacting free case, basically you will see terms like your kinetic energy, and there's no couplings like P1, P2, or things like that. Okay. Okay. And for the spin system, maybe you will see the coupling between the external field with individual spin. But if there's no sigma I, sigma j term, it is also considered interacting free. In principle, it could be very complicated. For example, maybe you could have things like here's the possible interactions. Okay, so for the particles, maybe there's a potential between the ith and jth particle. For example, maybe they have some kind of Coulomb potential. So basically, it tells us that what Ri is doing changes the behavior of Rj by the interaction V. So it's interacting. And for the spin system, you might have some crazy terms like this, where the behavior of sigma k depends on what sigma I and sigma j is doing. So we will focus on the non-interacting physics, which means that each degrees of freedom basically cannot see what other microscopic degrees of freedom is doing. Okay, so now we will start from another very important example, which is the classical single mode simple harmonic oscillator. Let's assume that we are in 1D. So the corresponding Hamiltonian is simple. It is just you sum over the energy for each oscillator, and maybe I should use this notation. And here, for each oscillators, we will have the kinetic energy and the potential energy provided by the restoring force. So basically, you can think of something like a particles that's oscillating back and forth. And then we have n of such oscillators. Okay. And each oscillator has a natural frequency, basically omega naught square is equal to kappa divided by m, where kappa is the coefficient that describe the magnitude of the restoring force. So you might wonder, like, is it just a pedagogical example, or there are some systems that really is described by such a simple model? It turns out that it is possible to realize this in maybe some of the atomic simulator experiments. And the idea is that you can use something called optical lattice. Okay. And the idea is that you try to counter-propagating lasers. And because they are counter-propagating, what's going to happen is that they will form some kind of standing wave where effectively this is the electronic potential that's given by this laser field. This is basic, and that's basically the idea of optical lattice. Okay. And for this kind of laser field, they are able to trap some neutral atoms at the potential minimum. So these atoms, when the temperature is low enough, they will basically moving back and forth in the local minimums. Okay. And if you try to approximate the potential profile locally by some kind of quadratic potential nearby the equilibrium position, then you will get this kind of settings that the system is described by a bunch of simple harmonic oscillators. Okay. And because these neutral atoms they don't interact with each other strongly. So the whole Hamiltonian can be well approximately by this expression that we just write now, where each particle is just doing their own business, basically behave like a simple harmonic oscillator. Okay, so now we should be able to write down the partition function for this system. So the partition function of this system is described like this. Basically, we integrate over the possible microscopic configurations, because now the degrees of freedom that we are identifying is the position and momentum of these individual atoms. And because we approximate the energy or the potential energy as some kind of quadratic potential, so the total energy is basically described by the harmonic oscillator Hamiltonian. Okay, and once we know what is the corresponding energy for the microscopic degrees of freedom, if we are considering the canonical ensemble, which means that the system is kept at a fixed temperature, then what we need to do is to write down the Boltzmann factor and try to sum over all these Boltzmann factor. Then we will get the corresponding partition function. Here I'll use J to represent the label for the particles. Okay. So this is the partition function for this system. So here's the question. Why there's no factor of 1 over m factorial? Okay. And the answer to that question is related to the fact that even we are dealing with identical particles, can we label those particles by some method? Okay. So in the ideal gas model, we have this 1 over m factor, because 1 over m factorial factor, because we are not able to label those particles, since they could come very close with each other and change their position. Therefore, they are indistinguishable. That's why we have this 1 over n factor. And here, we are making the assumption that the particles are not going to have significant wave function overlap with its neighbor, which means that more or less the region that this particle can appear is nearby its equilibrium position. Okay,